All right, so let's get started because I want to be able to give you an assignment for the weekend. Let's go. So basically, next. Let us consider the general case of a tapered structure in two directions. Okay, that's what we kind of talking yesterday. So here's a bunch of figures. So I do a very general figure. I'm sure you can do a much better figure than me. So let's say here you see I can put 2, and I do a general geometry. So you see here is 2, 1. Let's say here you make it whatever very wide, and here you start from here. And we do something like this. So you can have here stringers if you want. Okay, and well, you could have here stringers. And so on. But basically what I want you to see is that this is the, this will be, let's say, the Z, Y, so it should be the X then. And the X should be somewhere, and the X should be like this. It doesn't matter, really, the way the current system is. It's just a figure, okay? So basically, the thing I want to show you is that this can be tapered on the, basically on the Z direction, no? All right, I can be tapered on the Y direction. Okay, and all these can be subjected to all type of loads. Let's say it could be subjected to bending moments, F. This could be subjected to Vy. Let's say it could be subjected to a Vx. All right, and we could have, let's say, a bending moment Mx, and so on. We could have a bending moment My. And we could have even torsion, okay? But let's just leave it that way. Okay, and let's say this will be 1, 2, 3, 4, 5, 6 will be R, 1, 2, 6 will be the stringers or flanges. Okay, so it's the same procedure as we did before. Then if I remove, let's say, you're gonna have here now. So the problem is that you might have to end up doing 2 figures, so one for each plane. So for example, let's say let's first work on the plane X and Y. Okay, and then we'll be working on the plane Y and Z. So let's see. Yeah, I can make it fit. Why is that zoom stuff right in the middle? All right, so basically I'm trying to show this, okay? So basically what I want to say is that, let's see, if you look at the figure, the YZ, this plane here, YZ represent the taper in what direction? It will be on the span-wise direction, no? Yeah, and the YX represent like the wing can be wider at the fuselage and it's going to be thinner or shorter at the end of the free flow, no? Okay, so this is the taper that you can see. Okay, so what happens is that each one of those stringers, if you model it this way, we do an easy figure. So it's not going to be like before where it was only taper in one direction. Now you might have to do this in 2D, so it means twice. Okay, so this will be here. Lambda x. Okay, so here we have the force will be BR. We have here a px sub r. We'll have here a py sub r. And as before, let's say we call this here alpha r for the stringer sub r. We could say that tangent alpha r will be equal to delta y over delta x, where the delta y will be then this height over here. Okay, so basically you need to do with the stringers that will be changing both directions. So doing similarly, this would be now instead of delta x, it would be the delta z. We have here again a p sub r. This will be the py sub r. I might do it differently this time. This will be the pz sub r. This will be the alpha sub r. And this time the tangent alpha sub r will be delta y over delta z. What this will be delta z. And this distance here will be delta y. Yeah, why showing me this all the time? Do I need to admit somebody else? I think they all admit it. Okay, now there's 7. That's what happened. Okay, guys, sorry for not meeting you, but I wasn't looking at the screen. So if you want, let me go back. We are studying this study for the paper. So this time our cross section can be changed in length. So if you look from the top, let's say it can be this way, the wing. Okay, it can be taper along the length, but also along the width. Okay, for this type of product. So basically, I'm just summarizing the same procedure that we did before, but we had a constant value. So remember when we did this, we said that we had 2 different cases, case 1 and case 2, no? Okay. So following, I'm just going to do the derivation for the more general case. So the rest of the derivation follows case 2. Which is what? Finals effective in resisting shear because is the most general. Okay, so remember the case one, case two is that the one that we calculated the stresses, and then we said that the load, the actual stress was equal to the bending stress times the area of the boom. But in this case, I do the general equation. Okay, so this is a general structure, unsymmetric. So if it's unsymmetric, what does that mean? That you can have IXX, IYY, and IXY, no? Okay, plus the IGZ and so on. You can have moments on the X and Y direction. All right, you can bend your wing to go up and down, or you can bend your wing to go side to side, no? Okay, so that means that if we need to calculate then the stress, so the expression for the bending stress, sometimes they call it the direct bending stress. And this should be equivalent to the one that I give you on the document, should be equal to what? So remember, I use Z because the stress will always be axial, no? Axial is along the length of the beam. So this will be equal to what? Is the long expression My IXX minus My IXY divided by IXX IYY minus I square XY. All this stuff times, wait, I'm gonna have here an issue. I'm gonna check something here because I don't think it should be the same moments, but this should be equivalent. This equation should be the one that I gave you on that handout. So let's look at it. Probably would have been easier to go to the website, to Canvas, but let's see. Sign convention equation. I put this document, I know on Canvas side. I don't recognize one of the moments. That's why I'm going to double check. This equation here, remember, this is a sign convention. Okay, this should be equivalent to this equation. So it's My Mx. Okay, so one is Mx. You see this one? I put M1 should be Mx. So just copy this expression here, and I'm going to copy on my page. So My, this should be Mx. IXY plus, let me remove the cursor, plus Mx times IYY minus My IXY divided of IXX IYY minus I square XY times Y. Okay, or you could write it under this form. You see you have different forms, okay? All right, so let's go back to this. All right, so using this equation, then we say that the axial forces in the stringers slash flanges will be equal to what? PZ of R is the same procedure as before, will be equal to the sigma Z sub R, so for each one of the booms, times the area of the booms. So basically, now that we know this, let's say this is cantilever, you can find what is the stress at 1, 2, 3, 4, 5, 6, no? Okay, at different length of the, at different locations of the wing. So, but let's say we just make one cut. Okay, so let's say at this location, there is the moments. You can find what is the stress. So it will be the axial force will be equal to this. So following the same notation as before, if you know the axial, you can find the Y sub R by using that relation P Z sub R tangent alpha sub R, but you know that I like more to use the P sub R, which is the delta y sub r over delta z sub r. Yeah. And then the px of r will be something similar, will be the py of r tangent alpha r, so will be py of r delta y of r, so same expression, delta x sub r. Yes.
Look at the PYR equates to the delta YR over delta ZR. So we have the PXR, which is equating to the delta YR.
Yes, this is correct, because remember now this is taper, so that this can be taper in both directions. You see, this one is a delta y delta x. This would be the delta y delta z. That's the difference from these two.
Messing me up with having the Y on top of both. That other side.
Yeah, it's the same as here. You see, this will come from here, these two terms. Okay, for each one of the stringers. Okay, so basically it's the same. What happens is that when you start doing the calculation, this can become a mess. Okay, so now let's say the external shear forces Vx and Vy are resisted by the panels and corresponding PXR or PYR components. So basically, what does that mean? Is that the structure, which is this one, okay, this one, we have the shear force. So this one will be the stringers that will be on the direction of the load will be resisting the shear force, but not only the stringers, also the skin, no? Because that was case 2, correct? Okay, so what does that mean? Is that if we use the expression as before, I say it's easier to do summation of forces equal to interior. I just use the magnitude. We can say that Vx will be resisted by Vx wing or P. I don't know how to call this one last time. Did I call it P or W wing? I don't know. Plus the summation of all the stringers in that direction. So 1 to R of the Px of R's. And Vy will be the same thing. Vy wings, so the panels in that direction, plus the summation from 1 to R to the Py sub R. And here, remember, I will say, note, it's a lot easier to work with magnitudes, no? Okay, in other words, what you can say is that if somebody pull your hand, this should be counteracted by all these terms, no? So all these terms should be adding up. Not really one can add and the other can subtract, no? This will be the external, this will be the internal. This is the external effect, this will be the internal, okay? All right. So once we have that, so this is next. the shear flows in the panels are obtained from. Okay, so I want to do this in 2 pages. So let's say from obtain as follows. Let's say here as follows. Okay. Okay, so let's say step 1. I'm just going to put step 1. Solve above equation, which is these ones here. I mean, I can do it for V X wing and V Y wing. So basically, what would that mean? V X wing will be equal to what? Vx minus summation Px of r, 1 to r, and Vy wing will be equal to Vy minus summation of Py sub r. Okay, all this stuff is just the equation, but when you do an example, everything's become more clear, okay? So this is the procedure. So now that we have the force of the shear flow on the panels, what can we do? So okay, so let's see what did I write over here. Okay, using the shear force, the forces Vx wing and Vy wing in the panels, the shear flow is calculated using, so have fun over here. So let's say here this will be so let me just call it now Q bar, okay, will be equal to what? Minus, and we have a long equation here, Vx wing Ixx minus Vy wing or skin Ixy. If you look at it, this is related to the one of the bending Ixx Iyy minus Ixy square. This should be times xTds plus the summation of the b sub r x sub r. Now we need to do the other ones, which will be Vy wing Iyy minus Vx wing Ixy divided by Ixx Iyy minus I squared xy. And now this should be yTds plus the summation of the b sub r y sub r and here I'm going to put plus q sub naught. So remember on the procedures before, if the so this is the expression we have. So basically, this is a continuation of what we did before. Okay. what you had on the exam. Okay, but this time the box can be paper, no? So let's see. Let's see. Okay. So for an open section, what would be Q sub naught? Remember what was Q? Q sub naught for us on the procedure we have been doing all the time. No? So if the cross section is open, what will be Q sub naught? 0, no? Okay. And if the cross section, this would be Q sub naught would be different than 0. And let's over here. And so let me go here. So for closed section, the Q sub naught is obtained by doing what? What did you do? By equating external and internal moment, no? Then if it was statically indeterminate, we needed to add one additional equation, but this will be the normal procedure, no? Okay, so now here comes the little problem. So let's go here. So let me do here that we have summation of external moments equal to summation of internal moments. So if you want, instead of me doing the figure, because I don't have that many colors, I'll just show it to you. And you do the stuff. Yeah, that's why. So see, so basically now what's gonna happen is that all the different forces, the PXR, DYR, will also be created in a moment, no? Okay, we'll be creating also an internal moment. So if let's say you have the external forces Vx and Dy about point O, what will be the moment created by the external forces? It will be Vx, this one times the distance, eta sub naught, minus Vy times the xc over here sub naught, no? This will be all the external, correct? And now what we'll be doing the internal, in addition to the flows, also the forces on the stringers will be creating some internal moments. So basically you end up with this relation over here. If you want, you just copy, you can do the figure and copy the rest of the page. I'll give you a few minutes to do that. I'm going to pause the video because I don't think it's fun on the video, just to have